Hello, I thought I would try doing a lesson this way this week. So I really appreciate your feedback. Do you find it beneficial, or is it something you would rather I didn't do? So please do let me know either way if you prefer this or not. So this week, as you can see, we are going to cover the outcome 8 AC theory. We're going to start revising it this week. It's a really big outcome. There's a lot to it, as you all remember, all those lovely equations that you have to remember. And it's so big that I've split it across 3 lessons. So for the next 3 weeks, this is what we're going to be covering and revising. With that in mind, I would like you to get the notes that you were given in college and make sure you've got them in front of you when you're going through this lesson. So if you haven't got them now, please pause the video, go and get them, the handouts and the PowerPoint slides you were given, and have them in front of you, and then come back and press play again. Thank you. Okay, so now you've got your notes in front of you, we are going to go through the objectives for today's lesson. And those are to recap the characteristics of an inductor and the equations that correspond with them. We're going to go through some calculations involving inductive reactance, and we're going to look at how to calculate the impedance of a resistive and inductive circuit, both mathematically and using a phasor diagram and what that looks like. Okay, so first of all, here we have our resistor and our AC supply in our series circuit. Now, resistors don't react to AC, okay? They are simple components, very straightforward, and they behave as if it's DC. And the same formulas apply, which is why I put Ohm's law there, a fundamental formula that you're all very familiar with. So that applies when it's simply a resistor by itself in the circuit with an AC supply. Okay, and because they're such straightforward components, it's a good opportunity to talk about the phase difference, because I think that term can throw some people. And the phase angle is referring to whether the supply voltage and the current are in phase, as in, do they peak at the same time? So you can see here, here's our sine wave, our AC sine wave of our supply voltage and our current flow. And they are both peaking at the same time. So that means there is no phase shift or phase angle. There's no difference between the two. So we say here then that there is a phase angle of 0 degrees because they are peaking at the same time. And this diagram is our phasor diagram. The length of this arrow corresponds to the magnitude of the current. So, for instance, if you were drawing it, you would choose a scale, an appropriate scale to the value of the voltage here. If it wasn't too big, let's say it was 5 amps and sort of 7 volts, then you could have 1 centimetre per volt, and you would draw it to represent that length. You would then draw this line to represent the magnitude of the voltage of a corresponding length according to your scale. Now you can see they're both on the same line, and that's because there is no phase shift between these two. And this arrow here is your direction of rotation, and you must always include this arrow when you're drawing your phasor diagrams. Now, the angle between the current and the supply voltage is phi, and that is your phase angle. Now, quick apology here, guys. I have been calling this theta. Theta is very similar to phi, except it has a horizontal line through it, not a vertical one. So I'm really sorry. I made that mistake, and it is called phi. So the phase angle is denoted with this symbol, the Greek letter phi. Okay, inductors. Inductors are simply a coil. They behave in the same way a coil does, in that you pass a current through it and you will get an expanding and contracting magnetic field. For those of you who are still confused as to how they work and what they actually do, why we have them, you need to watch this video. You will have seen this before if you were in my classes. It's the engineering mindset explanation of the inductor, and it's brilliant. It's really straightforward. So if you're not sure, please click this link. Now, all the links that I've included in this lesson, I've put onto your email so that you don't have to open the PowerPoint. You can go straight into the links from your email. Okay, so our inductors are denoted by this symbol L in our equations, and the inductance is measured in henries. And inductance is just a measure of how good that inductor is at inducing an EMF, at having an EMF induced in it, and that is measured in henries. So the bigger the henries, the better it is at being induced with an EMF. Okay, so here's our inductor AC coming in. There's our supply voltage. Now, inductors do not like change. Okay, they resist the flow of those electrons. They don't want them. And so the current is really slow to increase in an inductor. So you can see here, we now have a phase shift. The voltage starts, and then 90 degrees later, we have our current flowing in the inductor. And that is depicted in a diagram like this. We always draw our current on the x-axis. We use that, what we call as our reference. Here's your direction of rotation arrow again. Don't forget to include that. And the voltage is then at 90 degrees ahead of the current. So in this case, we talk about the current lagging the voltage by 90 degrees. And so we call it a lagging phase angle. So as I say here, inductors resist the current flow. They don't like change. And this resistance is called inductive reactance. And it's denoted by this symbol XL. And you'll see that coming up in an equation. Here we go. First lovely equation. You need to memorize this. So inductive reactance, our XL, is 2 times pi times F, which is our frequency, times L, which is our inductance measured in henries. Now we're going to dive straight in and go through an example question. Okay, now I know I'm going quite quickly through this. You've seen this before in your classes at college, plus you also have the ability, you can pause the video, you can go back and re-watch things, and you can have a look at your notes as well. So I am going to go through this at a fairly good pace. So our question: an inductor with inductance of 65 millihenries is connected to a 50 Hertz supply. Calculate the inductive reactance. So instantly you need to think XL, that equation, okay? And I've sorted out 4 steps that you need to follow with all of these questions. And I think it's going to help you on how to approach these questions. Some of them have lots of stages to them, and it can be a bit confusing as to what to do first. So step 1, we identify the equation that's needed. Here we go. XL is 2 pi FL. Step 2, identify each letter from the equation in the question. If you need to, do what I've done. Draw a circle and write the letter so it's clear in your mind which number goes where in your equation. Step 3, rewrite the equation with the numbers in the correct place. Now, we've got our 2 and our pi, which is in the equation. Our F is 50 from our question, and our L is 65 millihenries. Okay, that's why I've put 65 times 10 to the minus 3. You need to know that that is milli, okay, 10 to the minus 3. So you can either write it like that, or That's the actual number, 0.065. Either of these is correct, okay? But you must make sure you get the right number, that you haven't just put 65 in there. Okay, and putting all this into your calculator will give you the answer of 20.42 ohms. Okay, they're in ohms, reactance is in ohms because it's an opposition to the current flow. It's just like a resistor. Resistance is measured in ohms, so is reactance because it's resisting that current flow. Okay, so now we've got question 2. An inductor has a 60 Hertz supply and has an inductive reactance of 25 ohms. Calculate the inductance of the inductor. So this time we've been given the reactance and we need to calculate the inductor. So go to our 4 steps. Step 1, identify the equation. Same equation again. It's talking about inductive reactance and inductor. Step 2, identify each letter from the equation in the question. So here we've got our F is 60. There's our F. Oh, sorry, that's bad writing. And then we've got our inductive reactance here of 25 ohms, which is our XL. Okay, so now we need to rewrite the equation with the numbers in the correct place. Here we go. So we've got our XL, which is our 25. We had that from our question. Our 2 and our pi, and then we've got 60, which is our hertz, our frequency, and L is our unknown. That's what it's asking us to calculate. So immediately you can see we're going to have to transpose this formula, okay? Because we need to get L by itself. Now, at the moment, L is being multiplied by this block of numbers here, okay? So these are all joined by multiplications. And to get L by itself, we need to get this lot onto this side of the equal sign. So we're going to do the opposite. Okay, if we're crossing the equal sign, we do the opposite. And the opposite of multiplying is divide. So we rearrange the equation, and here we have our 25, and this bulk of numbers here comes underneath to be divide. And that's going to give you what the value of L is. So L is either 0.066 henries or 66 millihenries. Right, so now I want you to pause the video and I want you to try this calculation by yourself. I want you to calculate the inductive reactance of the circuit. Once you've found an answer, press play and the answer will be on the next slide. Okay, so have a go. Right, so did you get 23.56? If you did, good job, well done. If you didn't, rewind the video a little bit and have a look and see where you went wrong, and make sure you converted the millihenries correctly, and then just check and make sure you know how to get the correct answer. So once again, I want you to pause the video again, and I want you to go and click this link which I've put in your email and join this quizzes and recap your knowledge of what we've covered so far. It should only take you a couple of minutes, but I'd like you to do that now, please. Okay, so thank you for doing the quizzes. That will really help you to remember those equations. Now we are going to move on to impedance, which is measured in Z. Sorry, the symbol is Z, is measured in ohms. And this is the total opposition to the current flow in a circuit. And it combines the resistance and the reactance. So we use this when we have both resistors and a reactive component in an AC circuit. And you can see here we use a good old right angle triangle to calculate this value. We put our resistance on the 0 axis on here on the horizontal, and we put our reactance going vertically. Now, we can use Pythagoras to calculate the value of Z. It's a right angled triangle, and his rule applies. And there we have phi, which is the phase angle or phase shift between these two signals. Okay, and that's the letter phi again. Okay, so here we have a resistor and an inductor in a series circuit. And for this example, the impedance triangle is drawn like this. We have phi, our phase angle here. We have our resistance. The value, you could put a value here for the letter R, and you would put the value of the inductive reactance up here on this length here, and then you can calculate or measure even the value of Z. If you've drawn this to scale, you could actually measure this length and you would have the value of the impedance. So that's an alternative way of finding the impedance if you don't want to do the Pythagoras theorem equation. You can draw it to scale if you're given the values, and then you can measure it. Using all of these equations, we can find these missing figures. Okay, and we're going to move on to an example that's going to show us that. This equation at the bottom I've introduced cos phi. So that is the phase angle, as you know here. Cos phi is also a power factor in the circuit. So it's a measure of how efficient that circuit is. And we calculate it by using the adjacent, so the length of the line which is adjacent to the angle, divided by the hypotenuse, which is our impedance. So we can put resistance over impedance, and that gives us our power factor. I'll cover power factor in more detail maybe next week. Right, so now we've got example 3. So we've got a circuit which has a 230 volt supply, 50 hertz, and it's got a resistor of 25 ohms and an inductor of 0.05 henries. And the question's asking us to calculate the impedance and the phase angle. So step 1, identify the equation. Step 2, identify each letter from the equation in the question. Step 3, rewrite the equation with the numbers in the correct place. And step 4, rearrange the equation if needed. Okay, so let's do it. Step 1, here's our equation for impedance. That was the question. A was calculate the impedance. Right, values from the question in the equation. It's asking us to calculate Z. The resistance was 25 ohms. We need to know the inductive reactance to be able to calculate Z, but we don't know this. However, there is an equation that we can use to find it. So we have to go back to step 1 to identify the equation to find XL. Okay, so here we go. Here's our equation that we're going to look at now. XL equals 2 pi FL. Step 2 again, we need the values for each of the symbols in this equation now. So our F is 50 hertz, that was in the question, and our L is 0.05 henries. Step 3, put your values into the equation. Our 50 hertz and our 0.05 henries. And then we don't need to rearrange this equation, we can simply do the calculation and get the answer for XL of 15.7 ohms. Now we can use that value in the initial equation that we had to find the impedance. So we've got our value for XL here, which we've transferred over, and then we've substituted these numbers straight into our equation. So we've got our R squared, which is our 25 squared, plus our XL squared, which is 15.7 squared, And that gives us an answer of 29.5. Okay, so the second part to the question was to calculate the phase angle. So that was that letter phi, and it was the angle between the resistance and the impedance. And we use cos, the ratio for cos, which is the resistance divided by the impedance. We know our value for impedance, we've just found that was 29.5, and the value for resistance was given in the question in the first place, which was 25 ohms. So we've put our numbers into our equation, and cos phi is a 0.85 lagging, and it's lagging, if you remember, the current lags the voltage in an inductor. So this is a lagging power factor. So we've actually just found the power factor. Cos phi is your power factor. And that's telling you that this system's about 85% efficient. There you go, how efficient the system is. And the question was asking us for the phase angle. So we needed to find this letter phi. And we do that by using our cos to the -1 button. So we do cos to the -1 of 0.85, which gives us an angle of 31.1 degrees lagging. Okay, it's a lagging phase angle. And that was just a straightforward calculation using the cos to the -1 button on your calculator. Okay, so there are two answers. So I went through quite a lot then. If you need to rewind and go through it again, please do. Otherwise, if you're feeling confident and then you can attempt some of these questions yourself, that would be great. There's the link here for the assessment for this week, which I'd like you to go ahead and try now, please. This link again is in your email if you can't access it from the PowerPoint. Okay, so thank you for watching. Please let me know what you thought. Good or bad, I don't mind, I'd like to know. All right, and good luck with the questions, and I'll put feedback as always directly onto those forms. Just revisit the link and you can see the comments I made. Thank you.